Good morning, good afternoon, everyone. My name is Reza Majidi. I'm the CEO of ConsuNova. Today, we have a pleasure to have two of the strong brain in AI and ML certifiability. We have Martin Beeby from ConsuNova. He's the head of advanced avionics. And we have Dr. Luuk van Dijk. He's the CEO of Daedalean in Switzerland. Daedalean has been our clients for many years, and they are, especially Dr. Luuk van Dijk, as a pioneer in pushing and with EASA and part of EASA in roadmap for AI and ML. So I think you're going to be entertained. We have a lot of people signed up for this webinar. I'm the moderator. I'm going to try to monitor your questions and bring up the questions to our panelists. So you do have a questionnaire on your disposal. So please ask questions, and we stop at the right time to address those rather than waiting for the last minute. With that in mind, I'll pass the baton to Martin Beeby. We get started because we have lots of materials to cover, and hope you enjoy it. Thank you. Martin, all yours.
Okay. Yep. Thank you very much, Reza. So we'll just go through some preamble while the last few people join. So welcome to another one in our series of educational webinars. Today we're going to be talking about applying design assurance that we have in aerospace to AI. Just a very quick background on ConsuNova. ConsuNova is headquartered in San Diego, where Reza is, and I head up the European office based just outside of London. We have clients and customers and distributors all over the world. Just a few of the names of people that we work with on a regular basis you will recognize here. In terms of what we do, most of actually what we do on a day-to-day basis is working on real projects, helping with compliance, helping with engineering support and process improvements. And training is part of what we do, where we're able to bring our experience from real projects into our day-to-day training. Just a very quick view on where ConsuNova can routinely help. It's pretty much all aspects, all stages of the V cycle. We can help at different levels or different disciplines. So that's enough about ConsuNova. I'll let Luuk introduce Daedalean, and then we'll get into the meat of the
That's right. When I chose the name, I knew I was going to have to accept all possible pronunciations. I say Daedalean, but you're free to vary on this, as long as you remember who we are. We're about 100 people, many of them originally founded in Switzerland. We have opened up the Phoenix, Arizona office recently, where we want to build out our customer support and commercial activities. We have a data annotation office in Riga, in Latvia. We bring together people from academia and people from avionics, pilots, flight safety. ConsuNova has been advising us since 2 weeks before we actually incorporated, because we wanted to base our company on a healthy sense of what it takes to certify things with the FAA and EASA. If I can have the next slide. So the product suite we've worked on and that we are currently bringing to market with partner Avionics is a visual situational awareness suite that uses electro-optical cameras to answer the 3 fundamental questions that you have as a pilot flying in VFR, namely, where am I, where can I fly, that is, where are others flying that I should not fly into, and where can I land, arguably one of the more important aspects of flying. And it does this by applying modern computer vision, deep learning, and robotics to this problem. So if I can have the next slide. So for this, we didn't only have to design a box that can do computing. We also had to design the software, but more important, we had to develop with the regulator the theory of how to get the software certified. So that's actually the text that doesn't go with this slide, but it's close enough. I will say more about the other topics later in the talk.
Okay. All right. Thanks very much, Luuk. Just a quick note. This is our kind of proprietary information, so please do not reproduce it without our permission. But we hope you enjoy this webinar. Okay. So we're going to be covering these topics today, really at quite a high level in terms of we've only got an hour to talk about what's taken years to think through and come up with. So we're going to just start off with the background of what is design assurance and what it means, and then move into how we can do this for AI or machine learning, and what it kind of really means in practice. And there's a number of questions that people really ask. How can we trust AI systems? How can we go about certifying them? And what extra guidance and methods do we really need? So I'm just going to start off with a quick question to everybody, just to see at the start of this what everybody thinks. So let's just, if you can answer the question, I'm just going to launch the poll now. So, machine learning will never be certified. Agree or disagree? So please, please go ahead and make an answer, your current feeling, and gauge the current feeling of the audience. So we haven't included the maybe, so we're asking you to come down on either side of the fence here. So just a few more people to give their answer, and then we'll take a look at the results. Okay, so let's take a look at the results of that poll and see what it says. So 88% are disagreeing with this statement. So that's 88% people believe that we will certify machine learning based avionics. Okay, that's good. It means we're preaching to the converted already. So that's really good. Okay, so just in case you're trying to ask questions and so on, please use the questions tab to get any questions, and Reza can then interject and ask the questions on your behalf, and then Luuk and I can do our best to answer. All right.
Actually, Martin, there is one, Martin and Luuk, there is one question that has come up so far. It's a good question for Luuk to think about when he gets the podium. You can read the questions, Luuk, but I'm going to say it out loud. It says, if possible, can the panel discuss the involvements of the Daedalean ConsuNova providing their lessons learned from their practice in concept of design assurance in neural networks, in SAE, G34, etc. In some cases, it doesn't seem like the value provided in such cases and current information and activities are being included in the standards developments like SAE are actively developing. So maybe you want to think about that, Luuk, and elaborate.
Yeah, I think maybe let's get to the end of the webinar, and because some aspects of this will be covered as we go through. So maybe at the end we'll revisit this question and try and address that. So let's just get on and go through, starting from the very, very basics. And I'm guessing that the number of people probably already know this, but it doesn't hurt to to clarify what is design assurance and understand the fundamentals of it so that we can understand how to consider the involvement of AI or machine learning as we go through. So the first thing to kind of think about is, what is safety? Okay, and one of the definitions, and there are many definitions, but they're fairly similar, but the one that's used most commonly in functional safety standards includes this statement that we should have some freedom from unacceptable risk. And that concept of unacceptable risk means that we have to have some quantifiable assessment that we can use to determine if something is acceptable or unacceptable. So the concept of quantification of risk is a cornerstone of safety. And if we look at the current set of guidance that we've got in terms of systems and item development, everything starts on the top left-hand side with the input of intended aircraft functions. We need a definition of what exactly it is that we're providing to the aircraft or to the system. There's a concept of intended aircraft function. And the system development process looks at that intended function, comes up with some kind of system design that can then be analyzed by the safety assessment process using the methods in ARP 4761, provide feedback and iterate round through modifications to the architecture and so on to come up with an architecture that meets the required safety. And the methods that are in ARP 4761 are both qualitative and quantitative. And we usually start with the qualitative assessment first, and then based on that qualitative assessment, we figure out whether we should do a quantitative assessment, really to make sure that what we are doing in quantifiable terms is acceptable or unacceptable. The resulting system architecture then allocates effectively pieces of intended aircraft function to the items that are in the implementation, the items of either hardware or software. Go away and develop the hardware and software, and then that comes up with an implementation, feeds back into the system process for verification, and the final result is a functional system. There is an important aspect here, and this is that wherever we have complexity, it's difficult to determine actually what the probability of failure is. Okay, for simple things, we can, through testing and so on, we can work out what we believe the probability of failure to be. But as soon as we have something complex, actually there is the possibility that we are introducing design errors that aren't necessarily quantifiable. So in these cases where we have something that is complex, either software or complex hardware or complex systems, then we apply design assurance. And design assurance is really the application of a thorough engineering process that is designed to identify and eliminate errors from a design. Now, we should add that actually following that design assurance process does nothing to actually quantify the probability of failure. It just gives us evidence that we've done, to the degree necessary, a greater or lesser job at identifying and removing errors from our design. So the safety is actually assured by a combination of quantifying failure related to the components that we use and design assurance for the more complex aspects of our design. And we'll come back to this probability of failure and all alternatives to design assurance in a few slides' time. So everything that we do in terms of certification is driven by the regulations, and there's some key regulations that really drive the necessity for design assurance. And I've paraphrased these down to make them as simple as possible. And what we need to do is make sure that our equipment delivers intended function. And this also drives us to have requirements-based verification, because the requirements are what identifies what the intended function is. So if we verify we've implemented that, then we can demonstrate we've delivered intended function. And we need to do that making sure that we deliver not more than intended and not less. Okay? So this causes us to look for unintended function and to make sure that we deliver all required function. We also have regulations that need to make sure that we deliver the intended function under any foreseeable operating conditions. Now, to some degree, this relates to the environment in which we're operating on the aircraft, but also it causes us to think about how we can deliver our intended function under normal and abnormal conditions. Okay. So there's some real fundamentals here. Requirements are important in the process, and actually the managing of how those requirements flow into our implementation, and how we can also flow that information to our tests to be able to demonstrate that actually through traceability all of the requirements have been implemented, and we also have verification through tests and so on that we have demonstrated all our requirements have been met. Traceability is a key part. And the numbers here really refer to the regulations, because we have some regulation clauses, because we have some modification to Part 23, the numbers are 2500 and 2510, but for Part 25, Part 27 and Part 29, for rotor wing and commercial air transport, we have 1301 and 1309. So these are the regulation clauses that I'm referring to in the numbers. Okay, so just a summary of what design assurance is. It's a process that establishes a level of confidence that errors that could cause or contribute to failure conditions have been minimized. Okay, and the degree with which we need to apply this, the design assurance level, is derived from what the ARP 4761 safety assessment tells us. Okay, so I said I'd talk about probability of failure and design assurance alternatives a bit more. And I think it's important to note that actually for machine learning based systems, it is possible to compute and guarantee some probabilities associated with the function being performed. Yet we need to get further evidence to make sure that this, the use of these probabilities is an acceptable approach. We could do something similar for software and hardware, but it's currently really not feasible. And in terms of design assurance, there are alternatives like the overarching properties that could be used to more specifically identify what are the key aspects that need to be demonstrated. Okay, let's move quickly on to talk about what the certification challenges are. And the first one really is, where does AI fit within the flow that we have? And it's important that we understand that the definition of intended aircraft function is independent of the implementation. And because as part of our system development process, actually the allocation of that intended aircraft function to components within the system should also be independent of the implementation that we choose for those things. And that's why I've drawn the AI development below the dotted line that distinguishes, if you like, the functional development we have in our system development processes per ARP 4754A and the item development processes we have in DO 178 and DO 254. So really, the AI development will have some function allocated to it, but yet the implementation of that function is actually going to be performed in either hardware and or software. Okay, so the AI component is a kind of item. Okay, now we have design assurance for hardware and software, so clearly we should apply something similar to the AI development. And in terms of what we're going to be talking about today, we should clarify that when I mean AI, or when I refer to AI, we're talking really about offline supervised machine learning. Now, as part of this machine learning approach, we're going to generate some kind of model that gets implemented in software or hardware. So we need to implement something similar to design assurance, but for the process that generates this model. So let's get to the meat of it. How can actually design assurance be applied to machine learning? And understanding the process is important. So in terms of generating this model that's going to be implemented, we need data. Okay? And we need to make sure that the set of data that we use actually covers all of the normal and abnormal use cases that are driven by the requirements for the intended function. So we have a set of data that we're going to use to train this model. Now, clearly, in order to make sure that this model is good or not, we need another set of data that equally covers the space of requirements. And those data sets need to be independent to make sure that actually we are doing true verification. And then once we take this model and implement it in either hardware or software, we need yet another set to run against the implemented model, also covering the same set of space defined by the requirements. Okay, so we need a lot of data for both training, verification, and validation of the input. And Luuk is going to talk a lot more about that in the next couple of sections. So I'm rushing through this bit really to give Luuk as much time as possible to cover what I would call is the interesting stuff. Okay, so what we need to make sure of is that we take the key bits of design assurance, which is the delivering intended function, so using this requirement traceability, having requirements-based verification, and having a way of identifying unintended function, and also being able to cover normal and abnormal conditions. And we need to maintain these principles to make sure that actually we can have some assurance that the process that we've gone through has taken the right steps to identify and remove errors from the process. And in terms of thinking about this too, we also need to consider that the output of the machine learning development process is if you like, a model, but it's driven by the input data set. So we need to establish effectively requirements to data traceability. And this is where the concept of learning assurance comes from. And taking that picture that we had before, we can identify we're applying learning assurance to the ML item, and design assurance to the hardware and software that implement that model. And I've put the famous W inside the ML development process, because this is really the systematic approach that's being proposed for dealing with this. Okay, so at this point, I'm going to hand over to Luuk to really get into the details of how we go about doing applying learning assurance
Martin,
Okay,
there is
go
a
ahead.
question. Martin, there is
Okay.
a question on slide number 18, and the question is, you can read the question. It says, for a probability for association is functions by ML, were you referring in case of machine learning to its confidence outputs by the neural network?
Yes, that's effectively what I'm referring to there. Yeah.
Okay, thank you.
I have some more to say about that. My first comment is I can't actually see the questions.
Okay.
So I trust you that somebody asked those two questions that you mentioned, but I can say something more about that later too.
Okay. So, Luuk, I will move on to your section and go ahead.
Right.
We'll start with the first.
Yes, let's start with the next slide. Yes, so I wanted to show, thanks for outlining the problem and the context. I wanted to show two examples to dive a bit deeper into what we're talking about. So this is the case of using a neural network to find a runway so that you can provide landing guidance. Humans can routinely land on anything that looks like a runway. If you want to replicate this function in a computer system, you first need to have a camera, and then the camera needs to somehow be connected to a computer, and the computer has to extract this information from that image. I think this is and suppose we establish that this works on 92% of the images of runways that we take in Florida. How does that prove that we're going to not be much worse if we leave Florida or if the weather is bad? And if I can have the next slide, or actually I thought it was the previous. No, yes, we skipped a slide. If you go back one, go back 2 slides. I thought this is weird. So this was the first example that I wanted to show, but the video is not playing.
Yeah, let me try and get the video to play.
Because now I skipped an important step in my story. So, there it works. So this is the first system I wanted to talk about. This is a system that uses electro-optical cameras to see things that fly, so that you can give the proper right of way, or in other words, don't fly into them. Humans are supposed to do this routinely based on their eyes. Part 91.113 says that each pilot, irrespective of flying VFR or IFR, if conditions are visual, people shall remain vigilant. It's black again, so it runs only very short. And this is also an application where to extract this information from the camera, currently the only thing we know how to solve this problem in a computer is to apply a machine learned neural network. So now if we can go to the next slide again, here I was going to say, now we can go to the visual landing guidance. Sorry. So here I was going to say, this is another example. So here it does what I just said it does. And the first thing to realize is that on a single image, the neural network can be, X% accurate and can have a Y% failure rate. And typically, on a single image, these failure rates are in the order of 1% or maybe even 4%. So obviously, in terms of aerospace safety standards, that sounds atrocious. If you're worrying about 10 to the minus something, where something is 5 or 7 or 9, and here we have a thing that is wrong 1 in 25 times. It seems like a massive chasm of possibilities. So there are 2 things that you have to realize to make this part of a safety critical system. First of all, it would be very bad if we took a single image of a runway and then close our eyes and then try to land there. That's not how humans do it either. You have an approach and you keep looking at the runway that you know is there, and you expect to see it better and better, and you can monitor how much better you see it and how your precision improves. And if you don't, you say, I can't see anything, and you call for a go around, and you rely on higher level systems to deal with this. So the first thing to make a machine learning component work in a bigger system is to realize that the performance and the safety guarantees are at the system level. So you have to architect the system so that the relatively high failure rate on a single image is mitigated by composing this over a longer time. And then it turns out, as we have shown, that you can actually reach much higher reliabilities than you would expect naively from hearing about the failure rates in machine learning components. So the second thing is to guarantee that this, if let it be 1 or 4 or 8% failure rate on a single image for the neural network, that actually holds when you go and fly in the wild. And this is where I was going to say, so if you're not in Florida, how do we know that we can still land on the runway? And this brings us to the second point. I'm sorry, the next slide. It brings us to the next slide. Right. What you have to do is you have to show that your machine learning component generalizes to the real world. So this machine learning component will have a probabilistic output, but that in itself is not revolutionary or new. It means it's same as with a radar. Radar has a finite probability of detecting a thing far away in the sky or not, and so there's that finite probability of actually working. And with a camera on board, we're not going to see orders of magnitude better than a human. What we have over a human is that we can look at all the megapixels all the time. So we don't have the concentration spread problem, but we still have the problem that we need to that we have limited data to work with, very large input space with few guarantees. So to guarantee that this works in the wild, you have to make sure that you're evaluating this on an independent sample drawn from the same population, from the same distribution as in the wild. And you want to overemphasize the hard cases, and then you want to eliminate any biases that you may have in there. For example, there's a famous example from the 90s already where the US military thought that they had constructed a tank detector with a neural network, but it was in fact a fog detector because all their sample images with a tank had fog and without a tank didn't. So these biases can creep in pretty easily. And then what you do is you have a trade-off between underfitting something that's too simplistic or overfitting where you memorize your training set, but without capturing the underlying generality. And this depends very crucially on your data. If I can have the next slide. This is already this. Well, I have something that still goes to the previous slide. So Martin said you can often compute these probabilities, and it's not only the confidence output of the neural network, it's actually this performance on your test set. So you've sampled reality in a test set, you train the network in some way, you evaluate that the system as a whole works this well. We can calculate that, and this is a very luxurious and comfortable position that we can actually compute these probabilities. But for these probabilities to hold, we have to do something akin to design assurance. Namely, we have to assure that our data was properly treated and that our data set on which we evaluated allow us to draw these conclusions. So we developed this concept and this process in 2 projects with EASA, and in the remainder of the talk, I will do a flyby of the process that we came up with. But I wanted to give some context, and it's free for you all to study because these resources are online. So in 2018, we approached EASA, and we were invited to do a so-called innovation partnership contract with them, where we worked through this exact case of visual landing guidance and just tried to see, okay, what does it take to assure that it will work in reality? And so EASA brought in the safety critical thinking from the point of the regulator. We brought in the more academic approach, like, look, we can make this work. Oh, if that's your concern, we can do. So it was a very fruitful collaboration. The report was published on the EASA website. It was actually presented in the SAE 34, the work group 114. And then we did a follow-up project to cover some of the holes or some of the obvious missing parts a year later. So concept of design assurance for neural networks 2 was released in May 2021. And then last year, we did another project with the FAA, going through the visual landing guidance one more time, an example project trying to break it and trying to see in a lightweight way what this W-shaped process that I'll talk about later looks like. In the meantime, EASA published the first usable guidance, which we're currently using in an STC to bring the traffic detection to market, where this concept is, battle-hardened, true tested for the first time. All these resources are online, and I cannot. So each of them is roughly a PhD thesis worth of considerations, hopefully with a very practical aspect to them. And in the remainder, I wanted to take some time to fly by, if we can have the next slide, fly by what this process actually looks like. So, as I said, it's all very nice that you can compute probabilities, and if these probabilities are a bit worse than you would like, you can have architectural mitigation in your system to raise them to a higher power so that it all works out well. But to guarantee that this probability actually holds and does not have fundamental design flaws in how you train the whole thing, we have to follow this this process. And actually, Martin showed this in the verification of the data in the sub-slide. I think this process really covers the whole cloud part in the first slide where he showed the cloud. Next to the hardware and software assurance, we also have the learning assurance to make sure that the system as a whole works as intended. So it's a small modification of the V because there's an extra step, because we no longer write lines of code one by one by locking a bunch of engineers in a room with sufficient chocolate and coffee and requirements. But we let machine explore the design space, and we have to make sure that that happens properly. So let's dive into that with the next slide. So the bit above the dotted line stays exactly the same. So back in 2016, there was a discussion about, oh, neural networks, machine learning, AI, nobody knows how that works. It's a black box. We need new methods, and we really don't. I mean, not at the level of completely scrapping all the ARPs, and even the hardware and software standards still have they don't go away. This is on top of that. So we have our requirements of what the system as a whole is supposed to do, and we've allocated something to a component that we're going to machine learn. Okay, now what's next? What's next is the next slide. So first, we already narrowed it down. So we're not doing general AI that is, conscious and learning online and doing all kinds of things that we didn't even ask. We're talking specifically about the pretty straightforward case of supervised offline machine learning. What that means is we're trying to learn a function. And this is a function in the mathematical sense, more than in the system theoretical sense. It's a thing that takes inputs and has to generate an output. The inputs can be an image, the output can be, there's an aircraft here, or this is the central line of the runway. And we use pairs of labeled data to first to train, then to, as part of the training process, to validate if the training is going in the right direction. This all happens automatically. And then when we think we're done, we evaluate on an independent set. And to sketch it, we're going to learn the true value of a function plus or minus some error. And what we want is that this error is on average 0 and small, and distributed according to some friendly distribution, so that we can build the assurance of the rest of the system on top of it. And for that, it is essential that this training, validation, and evaluation happen on sets that match reality. So this is where the learning assurance comes in. If I can have the next slide. So just like, making sure your engineers have the right tools and editors and compilers and verification tools to get everything working, your machine learning engineer will sit down and get the tools to make a learning algorithm based on his or her understanding of the state of the art. And for that, you choose a training algorithm, which is basically the shape of a computer program that's going to fiddle all the parameters in our model. It's going to explore the model space. We're going to encode the requirements of the system in a so-called loss function. And this loss function, in a very precise way, is an exact encoding of the requirement we want this component to meet. So choosing what you consider good or bad and how you weigh the errors and the misclassifications is directly translation of your requirements. So you have to justify, you choose, you have to trace your loss function to your higher level requirements. This loss function is typically computed on metrics, which is different ways to quantify how good and bad things are. There are hyperparameters. These are aspects of the training algorithm that make it. What do you compare it to? Make the algorithm work better or worse. And then we assume to a large extent that the way you do this actual training is not that critical, and that qualification of the tool is going to be enough, because if you look at the process sketched at the bottom, we first choose the learning algorithm, then we run it on the training set, and then we see if it meets the performance criteria. And then if we don't, we're going to go back and fiddle with it. This is what our engineers do. When they say, okay, it's accepted now, then we have to do the final acceptance test for this model with test scores on the test set, which is held out from the training. And so in a sense, what's in the orange box could be to some extent a black box, because we're going to independently test it. And what's important for this, I use the word independently, it's the same independent that's used in DO 178C for independence verification, except here it has a very precise mathematical meaning. And one of the interesting consequences is that what you would normally do in software, when you find a bug, you find an edge case that doesn't work, you go back and you fix your software. You could be tempted to do that by, you find something in the test set that's not good, let me go add it to the training set. It's a very dangerous thing, because you now have completely destroyed the independence of your test set with respect to the training set. And since the test set is usually the most expensive thing to gather, it's a very bad thing. So this is a trap that you should avoid, and this we'll come back to that later. If I can have the next slide.
Luuk, we have some interesting questions regarding
already.
This is slide.
Okay.
Yes,
okay.
Absolutely.
Then let's go back to that slide and have the question. I don't see the question.
I don't know why, but I'll read it out to you.
Yeah.
On slide number 36, Martin, if you go back one, the question is, the software hardware only needs to be qualified. Which tool qualification criteria do you assume for that? Because you mentioned that it's going to be a tool qualification.
Right. So we assume that it's that's a bit, this is where the rubber is hitting the road in our current process. We assume that it's qualified in the sense that you should be able to reproduce it. So it should not be some random crap that you cannot reproduce. You should do, best practice type of tracing of, if I have this verification, I should be able to rely on, if I redo this process, I get the same verification. So it's fairly lightweight.
So you're saying, it's a tool qual 5, TQL5, according to DO 330.
That would be would be our opening proposal to the regulator in this process.
Okay.
And then and that's to a large extent because this next the testing on the test set, the held out set, is like an independent gate. And so to some extent, but what you do want is you do want reproducibility of what you just did. If you just if you're producing random numbers, it's going to be hard to explain why you should expect it to work. Did I answer the question?
I think so. I'll get the feedback shortly. Another question is, can the W-shaped learning assurance process satisfy FAA's intent for setting the future certification policy? If yes, how can you elaborate that?
I was going to talk about that when I get to my conclusions, but what I can say is, so we're currently testing this approach with FAA and EASA in a project under the FAA that's currently validated by EASA using these standards. We have an issue paper / CRI that has been accepted. The goal of the project with both agencies was actually, well, to put it simply, to see how far we get. And now with this STC, we will actually see how far we get. That also feeds into my answer to your the first question that you mentioned, the relationship to the working group. So we observe what's going on in the working group, and we are, hopeful and supportive. A group of 500 people that try to build consensus is obviously going to be slower than a hungry startup that needs to get something out to market as soon as possible before they run out of money. So we always expected to be ahead of the working group, and we hope that the things we find feed into the process. And so far, we have no complaints. I think it's always dangerous to develop a standard without actual implementations being out there. I mean, on the one hand, it's understandable that everybody in the industry wants to wait until the standard is there before they go and do something. We don't have time for that. But we also think that getting some things built and seeing if they meet the criteria that reality puts forth would help shape that process. So we hope to keep reporting to the working group and help drive them forward. I hope that answered that question. So now I should get back to my W, otherwise we're going to totally run out of that. So these are lumped together in the interest of time. There are 3 steps here. So we've selected our learning process. We're going to run it, and we're going to train this model, and then we're going to verify in this test step that it works. And then we have this model, and we're going to put it in the box that's going to go on our aircraft to do the thing in practice. So in all of these steps, there's ordinary software that runs and that you have to prove actually works. And so all of that bit of making systems in aerospace still uses all the things that ConsuNova can tell you all the details in great detail about. And there's more about this in the, I mean, there are some non-trivial steps in there, but I just wanted to highlight that this is a relatively straightforward part of the process. If I can have the next slide. Right, so then we put our model on the thing that's going to run on the aircraft, and then we have to check that it's actually the same model as the one that we got out of the lab, and that it has the same properties when we go fly it around in the real world. So this is a very important verification check that the properties we bred in the lab actually holds on the thing out in the field. And there are some steps you have to take. For example, it's not trivial that if you compute something in a data center on a GPU, that if you use a slightly different GPU or an FPGA to compute the same function, that you get even if you get small binary differences in the numbers, you still get the same behavior. That's not a trivial thing to prove. And here, this is also where you check that your real-time constraints work and you don't run out of memory. Thing is, for machine learning compute, for a neural network specifically, that is actually a pretty simple piece of software. You can code it without data-dependent runtimes, without data-dependent paths through the code. You can give hard bounds on memory usage up front. So that's all very nice. If I can have the next slide. So at the end of all this, we have to do this verification that we correctly treated this data with the respect it deserves, and that we observed this independence and did not accidentally leak some samples from one data set to another. And for this, you want to put in place a very hard traceable set of processes around your data management. So it cannot be a zip file that Bob has lying around on his disk somewhere, and then the FAA comes by and says, okay, how did you evaluate it? And you have to, I think it was this file. So this is in line with best practices for software and hardware development. And actually, what we found useful here is to borrow a lot of the process and terminology from DO200, which is about assuring that you treat your data with the respect it deserves. And this way you can close the loop that your, the steps you followed were followed in the way that the regulator is accustomed to. I think this may actually have been my last slide.
Yes.
Is there another slide?
No, this is your last slide, Luuk, and there's actually a really good question that I'm sure that you will like has come up, and I think it's something that's definitely worth addressing. So the question is, the AI is non-deterministic. How do you deal with that?
Right. So it is non-deterministic in a very specific sense. So first of all, it's completely deterministic in one sense, namely, if I give it pixel for pixel the same camera input, I will produce bit for bit the same output. So no non-determinism there. The non-determinism that emerges is because the input space is so big that the probability of me showing the same pixels to the camera are nil. There are very, 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 very many possible images. And this is exactly the reason why you want to apply a machine learning program, because if it was possible to, if the space wasn't that big, if it was much smaller, then the probability that I could define crisp boundaries between yes, there's an aircraft, no, there's no aircraft, would be a lot higher. So it's exactly to these problems that have an inherent randomness in them, an inherent probabilistic aspect to them, that we apply these machine learning methods because we cannot give crisp rules. So to call the system deterministic, I've said this a lot, is to misattribute the randomness. There's a very nice book about robotics written by Sebastian Thrun, who kicked off the whole self-driving revolution by winning the DARPA contest in 2005 or 6. He points out in the introduction of the book, it's called Probabilistic Robotics. And it says that if you want to create machines that operate in the real world, they have to be able to deal with uncertainty. So it is the problem that has this uncertainty, and we're making a system that can deal with that. So the system itself will have to fulfill its function with the levels of certainty we are used to in the aerospace world. And what we're trying to do with this W space is to give you a means to do that. And we can assume, we can argue convincingly that the system will work as intended if we do this evaluation on the test set properly on proper data. So I hope that answered the question.
Yes, it did, Luuk, and I think it also reinforces the importance of the data sets that you have, and the careful management of those data sets is obviously another key aspect. We've got another good question, which I think you will also like, which says, have there been any challenges already in certifying the AI, the computers running the AI with the aviation authorities? And do you foresee the certification being completed within the next 10 years?
Oh, I would hope the next 10 months, otherwise people are going to be really upset. So the reason we chose the traffic detection as the first function to certify is because it's really, there's a really clear connection between the performance of the neural network on a single image, including the false positives and false negatives. Is there an aircraft here or no, given that there is one, yes or no. So that matrix is called the confusion matrix. Is very directly related to the DO387 performance, the minimal operational performance standards for electro-optical detect and avoid. So at the same time, it's not EASA put forth that this should be a DAL-C system because the impact of too many false alarms or undetected absence of function is sufficiently major. It would contribute to a false sense of security, which reduces operational safety, and false alarms add to operational load of the crew. So this warranted the DAL-C, which is the smallest non-trivial level, for which we have to do all the work in the first usable guidance. So we see this as a beachhead into certifying a machine learning component for an actual clear case, and also with a clear safety benefit, because we can easily see that we can easily show that we see way more than humans do, right? So at that point, if we can actually make that argument stick, we see this much, humans only see this, and we are really sure we see this much, then you have a pretty, you have no good reason to refuse that system's entry to market. So we want to start there and thereby test drive this process. And if it's not certified within 10 months, I'm going to be extremely grumpy at some people.
I am pretty sure you're well on that. I'm pretty sure you're well on that track, Luuk. Most definitely. So we've got another good. Oh, sorry. Yeah, go ahead.
No, go ahead, Martin. We're getting a lot of questions, which is good. Go ahead, Martin.
Yeah, so there's another good question, which I think is also another thing to touch on. And the question is, does the panel believe that the process defined in the presentation could also be used to certify DAL-A system? If not, what's the highest DAL you think the process will satisfy? Will we have a learning assurance level similar to a design assurance level with increased objectives?
Yes. So this is where I strongly believe that we can actually be better than classical software and even classical hardware development. Because if we treat the data right, we have reason to believe that the epsilons and deltas we compute are valid. And then it's a matter of making them smaller. So if we can, for the DAL-C traffic detection, we're doing this amount of work with this big a data set to prove that it meets those bounds. It's a matter of getting more data. So one thing we expect is that you first certify a system for certain uses to DAL-C. You put it out there, you collect operational data, not just from when it went wrong, not just a flight recorder that records the last 10 minutes before the crash, but you continuously record the data also in nominal operations to establish tighter and tighter bounds. And then when you do that, you have the means to make your next generation to DAL-B and your next generation to DAL-A. So I don't think that these data sets necessarily explode. For example, there are 50,000 runways in the United States, order of magnitude, if I'm well informed. So that's not really big data compared to what YouTube uploads, and it's not even big data compared to sampling the road network for Google Earth or Maps or driving directions or training your self-driving car problem, which incidentally is a much harder problem than flying. So I think we can sample these 50,000 runways in different weather conditions and different angles, different times of the day, to sufficient extent that we can get this visual landing system to DAL-A, including, you have to realize that's the whole system. So that's a system that, like a human would say, I don't think I see anything. We're going to do a go around and find another place to land because visibility here is crap. Or there's some dirt in my eye. Fortunately, I have another eye, so that's redundant enough. But a human pilot who loses both eyes in flight, has a big problem, which I suspect happens more often than once in 10 to the 9. Well, not sure. Losing a pilot, I think somebody computed a human pilot is 10 to the power 5. So I think we can. Long story short. I think for DAL-A here, we're actually in a better position than for software because, with all the extra work you do in the DO178C, at the end of the day, nothing guarantees 10 to the 9. And, things that are supposed to happen once in 10 to the 9 hours happen daily. So I think there we're in a strong position.
Yeah, I think also Luuk, if you... sorry, go ahead, Reza.
I'm sorry, Martin. Two kind of correlated questions, and we're getting a lot of questions. We have up to 28 now. We've addressed most of them. We've addressed most of them. So the questions are, why in the W shape process, the data verification is implemented at that stage, shouldn't be started right away. That's one question. So now, that's related to that. Are training, verification, and evaluation data sheets created in the same or different ways? For instance, one with real data others with synthetic data?
Very good questions, both. So this data verification, it's like, at the end, you have to collect all the evidence that you collected during the process. Like the V, you don't actually start the last thing. You prepare the records that go into the verification steps for later on, right? It's not that everything is started from scratch. So the data verification is where we gather all the evidence that we have collected along the way and take a good hard look to see if that's met. With respect to these three data sets, a very good question. So data sets are extremely costly to gather. And for training, you typically need orders of magnitude, easily 2 orders of magnitude more than you need for the verification or for the last step, the independent test. So what we try to do, and remember I said what happens in the orange box to some extent is free. So the only requirements really you have on what goes on in the orange box, it's not really a black box, but it has to be a model and a training method such that the generalization theorems hold. So it has to be a class of models that has the property that it can learn and generalize in some way. But the data sets, there you have a lot of freedom. So what we try to use is synthetic data. That's very hard because you find in the last independent verification step that your training algorithm picked up on all kinds of artifacts that you introduced. So it's tricky. It's not impossible, but it's very tricky. What's an easier way, which I recommend everybody starts doing, is to augment your data. So you take a small kernel of real data, which is precious and you can't use it again for testing, but then you use the simulator to change the lighting and the weather and to apply all kinds of noise to it. So that you have a much bigger data set and so that the machine learning algorithm can pick up on what's general and what's specific. And that's a much used question. So there the main constraint is that you don't pollute your training set with your test set, because that's cheating. That's that's the Volkswagen emission detector. This is also actually that's not a trivial point. This means, for example, that you cannot have the regulator put out a golden data set on which your system is evaluated. That would immediately defeat the purpose. Everybody would have a 100% score on this test set, and then you'd have no guarantees whatsoever. So this data independency is a very subtle thing. Sorry, Reza.
No, we have a few more questions. I think that because we're already out of time, and some people are actually logging off. Few people logged off.
We could,
so
we
I
could
think,
offer to answer them on the website in writing if there are. We could try
absolutely.
to.
I will send those questions to you and Martin. I will share those with you. And as Martin mentioned, these are learning kind of a webinars, right, and marketing kind of webinars. So we always get a lot of questions. I personally thank everyone for attending. We'll definitely address those questions. Martin and Luuk, so please close the sessions with your final word of advice.
Well, we were going to ask the question we asked at the beginning again, and see if we convinced any of the 3 people that were skeptical.
Yeah, let's quickly launch that and see what the answers come back this time. See if we made any progress.
Maybe the choir has dropped off, and the 3 skeptical people didn't even make it to the end.
Oh, I think I inadvertently terminated that. Let me try again.
Oh.
Is the poll visible, Reza? I'm not sure. I can't see from where I am.
No, the poll can be only shown once. So actually, you went down by 1%.
Oh, really?
Okay.
I think I messed that up. So yeah, sorry about that, everybody. It's operator error on my part. So
interesting.
Okay.
We convinced 1 person. Well. I hope that for the people that already thought it was possible that we give them some more insight into yes and how and why. Are we still there?
Hold on. Yeah, we're still there.
Yes, we are. Yeah.
Okay. So I hope it was still useful, even if you were the choir.
Yeah. Yeah, so I mean, as always, if you have any follow-on questions, and we'll do our best to try and go through the questions that have been asked that we didn't have time to answer, we'll go through those and get some written answers and circulate them back to the group. If you have any other questions, contact either Luuk directly or contact Reza and I at team@ConsuNova.com. Just a quick little plug, we've got some more end-of-year training coming up, covering ARP and DO processes that we outlined at the beginning, and you can get 50% off if you sign up using the code on this slide. So please join us for our next educational webinar, join us for our training sessions. I hope you found it useful. It's a massive topic that we've tried to cram into 1 hour, but hopefully you've all gained something from that. And thank you very much, Luuk, for your support today. As always, it's always great to hear you talk about the subject.
My pleasure, and thank you guys for your support over the years.
Thank you, Luuk. Thank you, Martin.
Thank you very much, everybody.